Okay, welcome everyone. So let's get started. So last time we talked about the fractional quantum Hall effect and how you can get a theory of the most important fractional quantum Hall states by the parton construction. There was also an interesting question, I'm sorry, I don't remember by who, on a particular parton state, the 1, 2, 2 parton state. And I posted a response in Slack. It turns out to be actually quite an interesting state, which people have studied, which may even have some experimental relevance. And in fact, it's an example of a non-abelian state, which is what we're going to talk about today. So, but any questions on our quantum Hall, any other issues with the quantum Hall discussion? Okay, so this lecture in some ways is kind of quite excited about it because it brings together, all the stuff we've been developing through the course of this semester. So everything comes together in the one beautiful package, and it gets a very exotic state, which has non-abelian statistics, which of course people are trying very hard in labs around the world to realize and control in the lab because of potential applications for quantum information processing. But here, let's just think about it as yet another phase that can be realized by our favorite systems on some lattice, which is spinor halves on any lattice, or bosons at half filling. We keep returning to that famous problem. It's the problem that keeps on giving. With all kinds of interesting phases. So our route to obtaining more exotic phases of spin systems has been this parton construction. Either you take your spin and write it in terms of bosonic partons S or fermionic partons F. And then this introduces in the simplest case a U1 gauge symmetry in both cases. And you ask what happens to that U1 gauge symmetry. So either it can be unbroken, and if you just get an unbroken U1 gauge symmetry, well, then things are problematic, and we're going to say much more about these unbroken gauge symmetries starting next lecture when we start talking about critical states. But so it's clear already if you have an unbroken gauge symmetry that you're not going to get a gap state, with one exception. Or you can break it down to Z2 by pairing the fermions. And then you get the Z2 spin liquid. So the U1 case we talked about. Or you can pair the fermions, and again, you get a Z2 spin liquid. So the exception for the U1 case was when you have the fermions hop in a band with a Chern number, and then you got the chiral spin liquid, which is rather analogous to the fractional quantum Hall states. It's in fact the fractional quantum Hall state of bosons at nu equals a half. It's the same structure as the chiral spin liquid. Okay, so now we have one case left, which we haven't looked at, which is what happens if you have both pairing of fermions. So that's why I talked about BCS there. You have both pairing of fermions, and you have a Chern number. What happens if you have both? That's the case we haven't considered, and that's what we talk about today. So now, when you pair fermions, we learned in superconductors, you get abricosal vortices. In spin liquids, you got visons. So we have these visons when you pair fermions. They have to be there. But now the question is, what happens if the spinons, which are the F particles, have a non-zero Chern number? So what happens if the spinons have a non-zero Chern number and you have visons present? That turns out to be the most interesting, and they're all interesting, but in some ways quite remarkable state. And in the context of spin systems, it was first discovered by Kitev using an exactly solved model. But I'm not going to do that here. I'm not going to review that solved model, beautiful as it is. I'm just going to present it in a way where you see it as an example of a quite, in principle, a very general phenomenon that could happen in all kinds of systems, spin systems anyway. Okay, so that's this chapter on non-abelian Ising topological order. So I guess, yeah, it was discovered by Kitev, and we won't consider his solvable model. Okay, so here's the model we're going to consider. Okay, so basically, also it turns out, yeah, before I get there, we're going to, which was the case in Kitev's solvable model, we're going to assume there are strong spin-orbit interactions. And the reason is essentially you want to lose the degeneracy of the spin-ons that's coming from a symmetry, which is the symmetry of spin rotations. If you have that degeneracy, then things go a bit haywire here. So we're going to assume there's strong spin-orbit couplings. And we'll take the limit of, where we just ignored spin entirely. So because of spin-orbit coupling, the spin-ons actually don't even have a spin index. All they carry is a Z2 gate charge. If you want to put in spin-orbit coupling honestly and really do the same thing in the spirit that I'm going to present here, that can be done. And in fact, Yanting has a paper where she's gone through calculations of that type. They're much messier, but you get the same physics that I'm going to discuss here. So basically, we have spinless spin-ons because of spin orbit coupled to a Z2 gauge field. So that's our model. So this is the Hamiltonian, very general class of Hamiltonians that we're going to look at. So you have these spin-ons, they can hop around from site to site, and they're also paired. So there's a hopping T and a pairing delta Ij. Now the spin-ons carry a Z2 gate charge, because if you remember for Schrödinger bosons, we saw that there was a charge of plus or minus 1 that was carried by the spin-ons. So now we want to really think about this as in a fully gauge invariant way. So we have to introduce a Z2 gauge field. So Zij is a field that sits on links of the lattice. And then we have, so you have basically, let me draw this out. You have let's say a square lattice. It could be anything in principle. And on every link of the square lattice, you have a qubit. So that's the Z2 gauge field. So there's a Z operator and an X operator in every link. And then you have the fermions sitting on the site. So every site has a fermion. It can hop around. So the fermion can hop from site to site. So when the fermion goes from here to there, F dagger F, to go from there to there, it has to, there's a matrix element for that that's called T. And then you have to have the Z operator there, because only then is it gauge invariant. Okay. But you also have another process where the fermions kind of, you take a fermion here, and it takes another fermion there, and they disappear into the vacuum. So that they become Cooper pairs. The fermions are paired, and they kind of disappear. And when they disappear, you get the amplitude delta X. That's the amplitude for the fermions to pair and become a Cooper pair. And then you also have to put a factor of Z to make the whole thing gauge invariant. And then for vertical bonds, we want to make we're going to have to take a certain pairing signature to get the right Chern number. This will be Z times delta Y. So that's the Hamiltonian in pictures. And here it is written out. Okay. So the fermions can hop from site to site with the help of a Z2 gauge field. And they can also pair, because this is a Z2 gauge theory. If this term wasn't there, it would be U1 gauge theory. And we don't want to deal with that. So it's a paired fermion state, just like in the Z2 spin liquid with a Zij. And then you have the usual Z2 gauge theory that we studied in great detail from the X and the Z operators. Here, L refers to a link. Sometimes I use the symbol L for a link, or the symbol Ij just depending on what's convenient. Ij are the two sites at the ends of the link L. Okay, so in fact, this is the theory for Z2 spin liquid. I mean, we could go back to our chapter on Z2 spin liquids where you had Schwinger boson, just replace the F's with S's, and this would be all fine. And in fact, this could also be describing the very same Z2 spin liquid we studied in the triangle lattice way back when. So naively, if somebody just gives you this Hamiltonian, you say, that's a Z2 spin liquid. So what's going to be new here, which gives you the exotic properties, is that we're going to take a certain form of the delta to get a Chern number. And that's really the key. If you have a Z2 spin liquid with a Chern number for the spin-ons, then something new happens. Okay, so any questions on the model, the definition of the model? So this is the model that we talk about in quite general terms for the rest of this lecture.
So
it's it's a version of the model that Kitea wrote down. Of course, Kitea wrote down very solvable, exactly solvable model. And then he also gave a lot of general arguments, which are the ones I'm going to focus on. Yeah.
So there was this argument that we assume some things so that our symmetry is kind of more symmetry group is restricted, like from U1 to Z2. Could you could you kind of elaborate on that? Like, what do we assume exactly?
Yes, sure. So so I mentioned two things, just to be clear. Here I talked about spin orbit. That has to do with global symmetries. If you have a global spin rotation symmetry, that's true symmetry, then these spin-ons will carry an extra index. They'll be doubly degenerate just by spin rotation invariant because they're spinners. And that leads to extra degeneracy that we don't want, as you'll see. So it's important that they be spin orbit so that there is no global SU2 spin rotation symmetry. Okay, that's point number one. And and in ruthenium chloride, where people think this may be realized, that's certainly the case. There's lots of spin orbit coupling there. Okay, the other thing had to do with gauge symmetries. So I was talking about global, but for gauge, yeah, so we have met two types of spin liquids. There's the U1 spin liquids and the Z2 spin liquids. The U1 don't have this term. This term is absent. And if this term is absent, as we saw in the previous chapter, this thing becomes a Z2 gauge field. And so if that term is absent, let me use, so this is not present, then this thing, instead of multiplying by this, you would have to put an e to the I times the vector potential of a U1 gauge field over there. And you get a U1 gauge theory. And in fact, that's what we did on the chapter on chiral spin liquids. And then you put the spin-ons with spin degeneracy in a band with non-zero Chern number, and we got the chiral spin liquid. So we are making two changes here. One is getting rid of the spin index. That's a global thing. Second is we're pairing them so that the only spin, the gauge symmetry is Z2. And so all you have, instead of the gauge field e to the IA, you just get the Z2 gauge field. So U1 gauge field, you get a Z2 gauge field, which is the Z, capital Z factor.
I see. Okay, thank you. And so if we solve this model and then we reduce delta, do we somehow morph one solution to the other? Are they completely disconnected?
Yeah, delta would, so the delta is now some fixed, it's not a dynamical field. So here the dynamical fields are F, Z, and X. Okay, so here's a model I've just written down, which I claim under certain conditions on delta is a fixed number, will realize this non-abelian phase. Now, yeah, so as delta goes to, when delta becomes exactly zero, then this model, well, it's still a Z2 gauge theory, but if I start from the original spin system, you would have to replace the Z2 gauge field by U1 gauge field. It would no longer be a faithful representation of the original spin system if you sent delta to 0, but you didn't replace this by a U1 gauge field. Then you're probably describing some other system that, who knows, but it would not be the system that D started with.
I see.
Would be okay.
Thank you.
Right. Okay, so every little piece here is something we've done before. We're just putting it all together, as you'll see. We studied this model. We studied the Z2 gauge theory earlier. We studied, the model with just these two terms where Zij was fixed, and so that this thing had a Chern number that gave us the chiral spin liquid with the U1 gauge field. We studied this thing alone on its own that gave us the Z2 spin liquid, and now we're putting it all together. Okay, so now how do we think about this? Well, the way we'll think about it is that as a function of the little g. When little g is very large, then the gauge field, if you remember, is confining. So all the link qubits just point in the x direction. The z is basically replaced by 0. And so for these f's to move, they have to form pairs, they confine, and you get what you'd call a trivial phase, where you don't have any fractionalization. So moving forward, if you want something interesting to happen, we're just going to, in fact, it's sufficient for most purposes just to think about the limit when g is very small. So when g is very small, then z is just a constant. So we can take various configurations of z. We could take z all, you could take z all 1. If all the z's are 1, let's say that's the case, where the z's are 1, 1, 1, 1, 1. That will be the ground state as far as the Z2 gauge field is concerned. Or you could take a more interesting configuration of z's, where there's a branch cut, and it's a -1 on the branch cuts. And now, of course, here, this is the famous Vis-on. So there's a Vis-on here, sitting right here, and it's 1 everywhere else. And of course, if you have periodic boundary conditions or anything, there has to be a second Vis-on somewhere else. Okay, so these are the two things we're going to look at. So we're just going to look at these two and ask, what do the fermions do in this background? So now it's really come down to a free fermion problem. You have different configurations of z's. Z's are fixed. You're going to take some delta ij, also fixed in some way. Just have to diagonalize the fermions. And remarkably, there's a lot of subtlety just in this free fermion problem. It kind of mirrors what happens in 1D for the Kitaev chain, but this is now I'm dealing directly with the 2D case. I think how you may have earlier on the semester talked a little bit about the Kitaev chain in 1D. So right now, so that most of today's lecture, I'm just going to talk about free fermions for these two different configurations of Z. Either those Z's are all equal to 1. That's the deconfined phase of the Z2 gauge theory, the ground state. And this is an excited state above some gap where you have a single Vis-on sitting there. And the energy of this Vis-on is of order, well, let's see, it's 2K, because there's only one plaquette, this plaquette here, where instead of getting a -K, you get +K. So the cost of that Vis-on is 2K, and G is very small. So we ignore that. All right, so now we just back to a free fermion problem. So let's deal with this free fermion problem first, where the fermion just move in the background of T and delta. Okay, so this is the these are the values of delta that I'm going to take. This is pairing of spinless fermions. So I'll take some value delta fixed positive in the x direction, and I times delta in the y direction. So this is sometimes called px plus ipy pairing. Why p? Well, because if you write this thing in momentum space, so let me just show that here. So if you write this in momentum space, so momentum space, you have something like f fi fi plus x times delta, and then you'll have f yeah, okay, so you have this term. Yeah, we don't need to worry about that. So if you write this in Fourier space, that becomes fp times f of minus p times e to the I p times x, p times one lattice spacing, so call that a, times delta. Now this thing is antisymmetric under exchange of the two f's because of the fermion anti-commutation relation. And so you can see this is the same as only the imaginary part will contribute, the f of minus p times sine pa. If you took the cosine, it would be just 0 because of the antisymmetry of the two of them. So this sine pa for small p looks like p, and that's why it's called p-wave pairing. So it's p-wave pairing with opposite signs in the x and y directions. Okay, so you take this this p-wave pairing here, and it has to be p-wave. Well, another way to say it, since the fermions are spinless, they have to be, since they're spinless, there's no spin to deal with. So there's the fermion wave, the Cooper pair wave function has to be anti-symmetric under exchange of the orbital degrees of freedom. That's the only degree of freedom you have. And so the orbital degree of freedom must be anti-symmetric and must have odd parity, which means it has to be p or some other higher odd parity angular momentum. On a square lattice, you only have p. So okay, that's so previously, yeah, if you form a S-wave superconductor, that you can only do for spins, for electrons when you have spins, where the spin wave function is antisymmetric, so the orbital wave function can be symmetric. So if you don't have spin, it has to be antisymmetric as p wave. Okay, so now you take this form of delta, and we go back to chapter 2 of this course. We're just dealing with Bogoliubov-Dijen Hamiltonian. Just take a Fourier transform of this Hamiltonian and write it in momentum space using this Numbu spinner, which we had also introduced way back when, of a fermion and an anti-fermion. You have to put a minus p here to make sure the whole thing carries momentum p. And there's no spin index. So when we did BCS theory, this was, there was a spin up over here and a spin down over here, but we don't have that. Okay. So that's actually turns out to be crucial. So you can write the Hamiltonian this way, and you can just work out what HBDG is. And okay, I've simplified it a lot. It's a 2x2 matrix, and a 2x2 matrix can be written in this form. These are the two pairing terms, the tau x and the tau y, the off-diagonal terms of the pairing terms. And this is the hopping term over here. Okay, but there's one crucial subtlety here, which is that because we don't have spin up and spin down, there's a double counting because various terms will appear twice. So for example, if I take the 1,1 component of HBDG, H11, it'll have a term like, from here, the dagger of this, F dagger P times FP times some dispersion FP. But if I take the 2,2 component of this, then I take the dagger of this, I will get F of minus P, and then F dagger of minus P. And this better be minus EP, as you'll see, because this is after fermion anti-commutation, up to a constant, which we don't care about. This is the same as f dagger minus p, f of minus p times EP. EP is an even function of p, and this is the same as that. So you get the same term in Hamiltonian twice, once from the 1,1 component and the other from the 1,2 component. And the same is true for the off-diagonal terms. So that's why there's this crucial factor of a half that we didn't have when we did the original BCS theory. And that's because of the fact that we're pairing spinless fermions. Another way to say this more formally is that this there's a kind of this psi p maps onto itself. If you take the dagger as opposed to take the transpose or the minus p, it's exactly equal to itself. So there is a, I don't know, you call it an automorphism where you can just map psi p to itself. And that implies that for the thing to be consistent, that H also has certain symmetry. It maps onto itself as p goes to minus p. And you can work that out. It turns out to be this. So if you take the Bogdahl-Dijen Hamiltonian at minus p and I take its transpose, that's the same as the Bogdahl-Dijen Hamiltonian at p multiplied by tau x and an overall minus sign. So I had just fun figuring that out. You can just check that that all works out. So this is just a matter of taking a Fourier transform of that simple free fermion model with pairing. And this is kind of a generic property of this. Okay. Another thing you notice, which we also had in the BCS theory, is that the energy eigenvalues of HBDG are always come in pairs. For every positive eigenvalue with energy E, there's another eigenvalue with energy minus E. In this case, for when you have momentum conservation, then it is just at the magnitude of this vector d of p, which is in the Hamiltonian. So you can think of it as, and the reason it comes in equal and opposite pair, because there's no term like tau zero. There's nothing like tau zero that's not there. So the eigenvalues are always in equal and opposite combinations. And that's a general property of a superconductor, has this particle-hole symmetry because you're mixing particles and holes. And in fact, you don't even need translational symmetry or momentum conservation to show that. You can write it out, see it more generally. In fact, for a mathematician, the easiest way to make the statement is when you have pairing like this, you can write each complex fermion in terms of Majorana fermions, which we will do in a minute. And that gives you an antisymmetric matrix. And there's I times an antisymmetric matrix. And there's a theorem that if you have an antisymmetric matrix times I, it has real eigenvalues which come with equal and opposite signs in pairs. And that's also going to be crucial, this feature, that the eigenvalues are paired because of this particle-hole type symmetry. That's going to be crucial to the topological properties and, in fact, the non-abelian topological order. Okay. All right. So far, I really haven't said anything that's shocking that, even BCS at some level knew about. I guess certainly when people started working on helium-3, when they started thinking about p-wave pairing of fermions, all of this was worked out. So everything I've said here was known to people as properties of p-wave superconductors. All right. Okay. So now let's bring something modern, and we're going to make things modern by introducing the Chern number. Actually, some of this was also known to the helium-3 people, but okay, it was kind of forgotten for a while anyway. Okay, so here we have just some fermion Hamiltonian, and momentarily let's ignore the fact that I'm double counting. Just think of it as some two-band fermion system. I can think of this as one band and this is the other band. Two bands are the same thing, but conjugates of each other, but let's ignore that. This is just some generic Hamiltonian of two fermions, of two bands of fermions. So what if this two-band system had one band with a Chern number? So this is two bands, so the Chern number of the lower band should be the opposite that of the upper band. So we're going to occupy the lower band, and that's the band you're interested in. So we're just thinking about, just mapping it to some other set of fermions, which I call Ca and Cb, and these fermions then just ordinary electrons, and they form this Chern number band. So we conclude that even when you have pairing, it's still possible to define a Chern number in 2 dimensions, and we ask now what consequences does that have? And it has some remarkable consequences. So you can work out the Chern number. Well, you can work it out the old-fashioned way, the way we did it for the quantum Hall case, or in this case where the band structure can be written in terms of just a vector. It has a different interpretation. This is like a single spin where P is some parameter that we're varying. So it's a spin moving in a magnetic field, a Zeeman field, given by the D vector. So the D vector is like a Zeeman field on this two-level system, which are just the two bands, and P is just the momentum that we're varying, which is just changing the direction and the magnitude of the field, the Zeeman field acting on this two-level system. So that we know has a Berry phase. It's just the area you map out on the surface of a sphere. That was the first thing we learned about Berry phases. So it turns out for this case, you can rewrite the Chern number, the usual formula for the Chern number that we had for the quantum Hall effect. You can also rewrite it as the Chern number of a spin and a half. And this is simply counting. In this case, the Chern number is counting the number of times this magnetic field, so this Zeeman field wraps around the sphere as you go over all the momenta. You have this two-dimensional momentum, Brillouin zone. As you move around the momentum, you're asking how many times does the magnetic field wrap around the sphere? And it's given by this integral. And for a certain range of parameters, it's 1. So this is what we're going to focus on. When it's 0, then you can go back. Nothing interesting happens. When it's 0, then you're back to a Z2 spin liquid, which we already have studied in great detail. But now we have this possibility. So you have these two bands that don't touch. Everything is gapped, but there's a Chern number. And this Chern number is for a band of paired fermions. Okay. So what are the consequences? Well, the consequences we have learned is that once there's a Chern number, there's an edge state. So there should also be an edge state here. But there's a little twist. Now we do have to remember that this involution on the Hamiltonian, that there's really, I'm double counting. So all these arguments I made, assuming that these were just ordinary electrons, where I ignored this constraint or equivalently this constraint. I just ignored it and just treated them as two bands of fermions, but they're not really, they're the same set of fermions. So I am double counting the degrees of freedom. So what you should get at the edge is half an edge state. Okay, and that's in fact what you get. And half a fermion is called a Majorana fermion, and you get half an edge state. Now, I think I could go through a more careful calculation to show you that, but I won't, because I'm going to go through that calculation in a different context. Well, if not today, then certainly on Wednesday. Doesn't look like I'll finish this chapter today, which is fine, because this is really in some sense, the most subtle chapter of the entire course. So we're just bringing everything together to get some really new physics. Okay, so I'm just going to assert without proof but just this hand-waving argument that you get an edge states, but you only get half the edge state. So let me make at least the assertion precise. And I have references here to various review articles. In fact, there's a nice review article by Alicia. You can read where it goes through the whole calculation explicitly. The calculation is very similar to the calculation that shows you that you have Majorana zero modes on the Kitaev chain. It's essentially the same argument. And I will go through an argument just like that in a few minutes. So that's why I won't do it here. So what do I mean? What is the edge state structure? Well, so what do I mean by half a fermion? So if I have a single, suppose I have just a single fermion, F. So this is what we now call a complex fermion, just to distinguish it from a Majorana fermion. What is the Hilbert space or Fock space with this fermion? Well, it's a two-level system in Fock space. Either the fermion is present, let's call that state 1, or it's empty. So you have two states, 0 and 1. So it's a qubit. So complex fermion on its own just describes a qubit. Well, whenever you have a qubit, you have the Pauli X, Y, and Z operators. And what is a Majorana fermion? It's basically the Pauli X and Y operators for this particular qubit. So basically you define gamma 1, which is F plus F dagger, which means you can either go from 0 to 1 or 1 to 0 and you take the sum. Well, that's exactly what the Pauli X operator does. Or you can put a minus I and take F minus F dagger. That's exactly what the Pauli Y operator does. So there's nothing, at least at the level of a single fermion, there's nothing mysterious about Majorana fermion. They're just the Pauli X and Y operators, which operate on the two levels of the qubit. What's much more interesting about them is that when you have two fermions, now if you had two qubits and you had an X operator for this qubit and an X operator for that qubit, those two operators would commute. But if you had two fermions, a fermion here, a complex fermion here, and a complex fermion there, and you make their respective Majorana fermions, then those Majorana fermions would anti-commute. So it's really, you have to be very careful saying that this is just like a Pauli X or Pauli Y operator. It isn't really. It's only that for a single fermion. But once you have more than one fermion around, then these are anti-commuting operators, even for different sites. So that gives them a kind of a non-local structure that's crucial to the whole game. Okay, anyway, so this is just a definition right now. Gamma 1, gamma 2 are F plus F dagger and F minus F dagger, which is some operators, Hermitian operators that we like. And you can, just like the Pauli operators, they're Hermitian, their square is 1, and they anti-commute with each other. I mean, for a given qubit, the Pauli operators do anti-commute. What's novel about the Majorana fermions that they anti-commute even for different qubits. Okay, so this is what I call half of a fermion. That is, a complex fermion is made up of two Majorana fermions. So one of them would be half a fermion. All right. So and what about the Z qubit? Well, the Z qubit is the easy one. That makes complete sense in any case. The Z operator is just 2 F dagger F minus 1, because on this state it gives you a minus 1, and this state it gives you a plus 1. On this state, minus 1 and a plus 1. That's simply 2 F dagger F minus 1. And knowing this, you can work it out. It's I gamma 1 gamma 2. So I gamma 1 gamma 2 is like the Z operator as eigenvalues plus or minus 1. And it's bosonic, of course, even for fermions. So that's not the mysterious operator. It's the X and Y that anti-commute between different fermionic qubits as opposed to bosonic qubits. Okay, so if I had an ordinary Chern insulator, but I didn't have this over double counting, then the theory of this is the theory of the edge state. We've seen this all over the place. This is the edge of a Chern-Simons theory. It's chiral latent liquid, right moving fermions only, now written in momentum space. And just for fun, I rewrite this using Majorana fermions. So I introduce Majorana fermions in momentum space, and now I have to be a little careful because the Dagger operation takes a complex conjugate, and momentum space you have e to the IPX factor. So when you take the Dagger, you have to put a minus p here. So there's little bookkeeping details like that, but roughly speaking, you take your eta p and write it in terms of its real and imaginary parts, the two Majorana fermions for each momentum p. And if you take a Chern insulator like this, you can rewrite it as what we call as two chiral Majorana fermions. So here's Majorana fermion 1 moving to the right, and another Majorana fermion also moving to the right, gamma 1 and gamma 2, with a velocity vf. Okay, so this is just a exact rewriting of the boundary of the chiral the chiral right-moving complex fermion. It can be written as two chiral right-moving Majorana fermions, which obey these relations. Yes, Juven.
Oh, hi, Subir. Sorry, I was just trying to add a comment about what you say about this, say, single fermion as a qubit.
Yes.
You said that certainly true that you can write this Majorana operator as one is gamma, the other is gamma 1, gamma 2 as a sigma x and sigma y. And you say it's very similar just for like a qubit. But there's a subtlety here is that the usual qubit or bosonic qubit has two states. Here, that two state is actually both are bosonic state. While here, the Majorana operator is actually x on one bosonic and one fermionic state. So in a sense, the gamma, the Majorana operator actually switch bosonic and fermionic ground state. Sigma x, sigma y switch bosonic fermionic ground state. So that's actually let's pay attention. Yeah, actually,
thank you for saying that. That's a very good point. Yeah, absolutely. It's saying more clearly what I was trying to say. So when you say it's a fermionic qubit, fermionic state, you mean that when you have two of them, then they have to anti-commute, which is basically what I was trying to say. So that's right, but that's a good way to put it. The Hilbert space, there's something called fermion parity, which is whether the state in the many fermion state case has even number of fermions or odd number of fermions. That's even with pairing, that commutes with the Hamiltonian, because the Hamiltonian only has pairs of fermions, so the Hamiltonian is always bosonic. But one of these states, let's say this one has even fermion parity, and then this one will have odd fermion parity, and gamma 1, gamma 2 form a fermionic qubit in the sense that it takes you from a state with even fermion parity to odd fermion parity or vice versa.
Yes.
Yeah, thank you. That's another nice way of saying what I was trying to say in terms of.
And also fermion parity will be the sigma z operator. And another thing is actually there's a hidden supersymmetry quantum mechanics structure which you heard about last week by Abi's talk. It's basically related to this fact. Even for the single complex fermion, the Hilbert space built on a single complex fermion or two Majorana, actually the structure is still different from a single bosonic qubit. Just the fact that the one state is bosonic, one is fermionic, and that's a subtle part.
Okay.
Right. Okay, that's
all right. Okay, thank you for that insight. All right, so where were we? Right. So I told you the edge state of a Chern insulator or an integer quantum Hall state is this, and we have this rough feeling based on the double counting in HBDG that we should take half of this. And then the advantage of writing it in half in terms of this way is that very easy to be very symmetrical about it and just drop one of those. So that's the claim. This is a statement about free fermions with p-wave pairing. It's a property of a BDG Hamiltonian that if you take an edge, then at the edge you will get a chiral fermion mode. And here you can also see why it was important that I get rid of the spin. If you had added spin, then you would get 2 chiral fermion modes, and once you took Majorana modes, and once you get 2 chiral Majorana modes, that's equivalent of a complex mode, so you don't get all this interesting physics. So the fact it's spinless is important to allow us to get just 1 chiral Majorana mode on the edge. And analogs of this result were definitely known to people studying helium-3 a long time ago. And you can derive it, just by solving the BDG Hamiltonian in the presence of edge. I did that for the Landau level way back when. We had a Landau level with some edge potential, and we solved it, and we found that near the edge there was a complex fermion edge state. You just do the same calculation for the BDG Hamiltonian rather than the Schrodinger equation, and if you just work it out, you will get. And many books and review articles work it out, and you will get exactly what I've just asserted, half the edge state of the integer quantum Hall effect. And that halving has very much to do with, as I've already mentioned, this factor 1/2, this relation of this Nambu spinor, and this property of the BDG Hamiltonian. Okay. All right, so we've already found something bizarre, although I haven't fully proved it. And this is the thing written in real space. If you have Chern number in a Z2 spin liquid for the spin-ons, then you can get half an edge state. You get a chiral Majorana fermion on the edge. Any questions? Well, there should be questions on this, but I don't think I'll get to. I'm not giving the full proof of it because the calculation I'm going to give is very similar to the calculation I'm going to do here. And so I'll just give it over here, which is the more surprising result, actually, this one. Okay. All right, so then let's get to the really amazing result, which also some analog of which was known to people in helium-3. So let's remember, so far I've just been dealing with fermions where the Z2 gauge theory was in its ground state. That was in this state. So we'd like to, and we found this strange edge state. Okay, well, you say, all right, there's an edge state, fine. But in the bulk, it's still a Z2 spin liquid. Z2 spin liquid has an E and an M particle. Is that still true? The answer turns out to be no. There's also a remarkable change in the nature of the excited states. So what we're going to take now is this Vizon solution. We're going to take Zij equal to this thing with a branch cut. So it's -1 on some cut all the way up to another Vizon somewhere else. And now solve for the BDG Hamiltonian in this configuration. And now I can state them in result. What happens is just like the edge state was cut in half. Here you find a 0 mode, very much like the Kitaev chain, where you have one fermionic qubit, that is one complex fermion, which is shared by the two Vizon. Let's imagine we just have only 2 for now. Half of the fermionic qubit is on the left Vizon, and the other one's on the other one. So let me say that in words. So what you find, yeah, okay. So I said that you could take a fermion C and write it as gamma 1 plus I gamma 2, and this fermion C defines a 2-level system. So it turns out what happens is that there's a very low energy, essentially 0 energy, 2-level system associated with every pair of Vizons. And this gamma 1, if this is the Vizon number 1, I have another Vizon number 2 over here, then gamma 1, is some linear combination of F and F dagger on the sites. So the Fij, so gamma 1 is Fi times some wave functions, multiplying them, some amplitudes. So gamma 1 is something like some function, let me call it f1 of x times, no, not f, sorry. There's too many f's floating around. Let's call it g of x. So g sub I times the operator fi plus some, it'll turn out to be, g star, I think it turns out. Yeah, g star of I fi dagger. And the important point of this g, which is the weight of the spin-on, fi from the original Hamiltonian, is localized very close to this vortex. And the g for gamma 2 is very localized very close to the other vortex. So there's one complex fermion, and its real part lives over here, and its imaginary part lives over there. That's the amazing result. And therefore, the Wison is no longer a Wison. It's or the M particle. It becomes what's called the sigma particle. And it has non-Abelian statistics. Okay. So that's the main thing I want to show you in this chapter. And Hao-Yu is going to say more about the statistics tomorrow in section also. But I don't know if I'll do enough. Well, okay, maybe Hao-Yu can review the parts that I don't cover today, tomorrow also. All right. So how do we show this? So does everyone understand the claim? So the claim is, anyway, that there'll be one fermionic qubit that will have essentially zero splitting. In fact, the splitting goes exponentially to zero as the Wisons move far apart. And that fermionic qubit will be made up of two myrnas, one myrna sitting here and one sitting there. So this is and that's the essence of why it's useful for quantum computation. There's this qubit, which is neither here nor there. It's both places. It's in some highly entangled state. And that's why, if you had some random noise, it doesn't affect the state of the qubit because it's in this highly non-local state, which is orthogonal to any random noises that you might apply. Let's see, there's some questions on chat. So Jovan Wang asks, is there a precise way to evaluate the Chern number of a chiral P-wave superconductor? Okay, I'm not an expert on this topic, but this is precisely the Chern. In fact, you just compute, as far as I understand it, you do exactly what I just said. You take your P-wave superconductor, you write it in this form, and just ignore this this property and just compute the ordinary Chern number, and that is the Chern number. So the Chern number nu equals 1 has an edge state, in this case of chiral central charge 1/2. So basically the only difference is for the integer quantum Hall state or the chiral spin liquid. The Chern number was equal to the central charge, chiral central charge. Here it isn't. The chiral central charge just half the Chern number, that's all. Now when you put in interactions, there's some differences. Somehow the Chern number mod 16 is what matters and so on, but I'm not going to talk about that. Let's just take Chern number 1. Okay. All right, so let me try to, well, maybe I'll stop here. Let me just say one more thing so that things will go a little more smoothly in the section tomorrow. Okay. So what I said is you take this configuration for a general Zij, and so you don't have translational symmetry. So in general, your Hamiltonian, so if you have M sites, your Hamiltonian is a 2M by 2M matrix, which is acting on the Fs and the F daggers. So it's like a BDG Hamiltonian without any translation invariance. So we can diagonalize it. How do we diagonalize it? Well, you do this, you take a linear combination of the Fs and F daggers. So we call the new fermions the etas and the eta daggers. And there's some unity transformation that takes you from the Fs to the etas. Okay, so notice that the eta are the same, just like the f's were the same, and that's a property where that's you're using the fact that this fact that just like in the originally that states with p and the f's and the f daggers really describe the same same term in the Hamiltonian, and that's also true after this unitary transformation. And furthermore, the Hamiltonian has to be particle hole symmetric. It has to get eigenvalues which are equal and opposite in sign. So in this new eta basis, for any general set of, let's take some even number of Wisons in an infinite plane or on a torus. Let's take it on torus, make it finite, m sites. Then the final Hamiltonian, I'll just assert, and this is a very general statement, can be written in this form. There's some set of energies, and they're m fermionic qubits. And this you can see is exactly the Pauli Z operator for each fermionic qubit. It's either 1 or -1. So the energy eigenvalues are plus or minus ES. And you have these m qubits with some values of ES. And S goes from 1 to m. So that's a easy to establish, very, very general statement of any BDG Hamiltonian without spin. Okay, so now the claim is, which I will not prove today, that when you do this for two Wisons, only one of these is very, very, very tiny. So if you look at the spectrum in the presence of two Wisons, so you have these energy levels that are equal and opposite. So where did I go? So here I have a Wison. So I have a whole bunch of energy levels. This is energy E, right? So typically there's some gap, which is proportional to delta. So this is of order delta. And then if you don't have translational symmetry, you get a whole bunch of levels here. They'll be equal and opposite. And this is 0, which is very special. And right near 0, you'll get only two levels. It's splitting epsilon 0. And this happens in the presence of two Wisons. So each pair of Wisons gives you two levels that are almost 0. Okay, so what happens when you have four Wisons? Well, then you find that there are 2 times 2 levels. And when you have 6 Wisons, you have 2 times 2 times 2 levels, and so on. So basically, when you have n Wisons, it gives you n over 2 complex fermions with essentially 0 energy, assuming they're well separated, which means you have 2 to the n over 2 states. So it's not as if each Wison has a bound state of a fermion. If a Wison bound state had a bound state of a single fermion, that would be the E particle, remember? Z2 spin liquid, the Wison binds a spin-on to get the other spin-on. So here, each Wison is binding half a spin-on. And that's called the sigma particle of the ITO. Okay. So now I have to, first of all, prove this statement that this is true. I won't prove it in great generality, but I'll show it in a simple calculation that you do get this near 0 energy 2-level system for a pair of Wisons. And then we have to figure out what are the topological properties of the sigma particle. Okay, so I don't think I'll finish that today. We'll talk more about it. You'll see more about it in section. I think maybe how you will cover the rest of this argument, but I'll repeat it in any case on Wednesday. Okay. Any other questions?
So I I have like two naive questions. So the first one is, at the beginning you mentioned something that like something is going to be non-abelian, and I kind of missed that, I think. Like where is
I haven't proven. Yeah, we're going to. Yeah, I haven't shown that at all. That's coming. So so what I've shown you is that there is this one Majorana fermion, at least stated. There's one Majorana fermion for each. There's one Majorana fermion for each Vizon. So here I have a system of 4 Vizons. And what's so normally when you take, we'll ask what happens when you take, say, gamma 1 and exchange with gamma 2. And then you exchange gamma 2 with gamma 3. It turns out that the order of operations matters. That's why they're non-abelian. If you first interchange gamma 2 and gamma 3 and then interchange gamma 1 and gamma 2, you get a different answer. That's what's non-abelian, that the order of the interchanges will matter to determine how the many body state changes. So that's why it's non-abelian statistics, because the order of braiding, as we call them, you have these different braiding operations, and the order in which you braid them matters. When in the previous things we have met in abelian Chern-Simons theory, it doesn't matter which order you take particles around each other, you just get a product with the phase factors, which is the same independent of the order in which you do the braiding. But I haven't gotten to that yet.
I see. And then another question was kind of like where so this model, like we wrote now, these F particles, like they're not necessarily like any sort of partons, right? There's like not, this can be just like fermions on a lattice or something in principle, right?
Yes and no. So for us, they are partons. For the state we're talking about, it's important that they're partons, because only because they're partons do they carry a gate charge. If they were just, if I just look at this thing, if I just throw out the Zij, then there's some odd, it could be electrons in a p-wave superconductor. But the case I'm considering, they are partons, and that's why we have this Z2 gauge field sitting there. They carry a gate charge. Only partons can carry gate charge. The physical electrons don't carry gate charges.
Right.
Emergent gate charges.
But
this particular theory, sorry, let me finish. This particular does apply to something called, to actual electrons in P plus IP superconductors, in which case the Vizon is a physical vortex. It actually is an Abrikosov vortex in a P plus IP superconductor. Now that system is not gapless, and it's strictly speaking, it doesn't really have topological order, but it does share this property that this non-abelian phase factor is the same. The non-abelian transformations, it's not a phase factor, it's a whole rotation, is the same. So yes, you're right, actually. Some of what we say can be transferred to ordinary P plus IP superconductors. But that's not the way I'm presenting it, because this is a much more robust thing in this model, because it's a fully gapped state. There's not all these subtleties about extra abelian phase factors you have to worry about. This model is a bona fide topological phase. With the P plus IP superconductor, there's a few caveats. Yeah, sorry, go ahead.
Yeah, so like related to that, I was kind of confused. Like, how should I think about the fact that we are kind of considering this spin-on Hamiltonian kind of on a background of some gauge configuration? Because like in principle, this is like a coupled problem of the full Hamiltonian, right? And this is not just like a gauge choice, because these are like physically different, like.
Absolutely, yeah. So that's related to this G goes to 0 limit. So at the moment, I'm solving it as G equals 0. Then you can make G non-zero and look at corrections and powers of G, and satisfy yourself that some things will change, like the You normalize the dispersion, you normalize the mass of some things, but this statistics that we're going to compute will hold to all orders in G. Yeah. So it's kind of fortunate that just fixing the Z2 gauge field already is enough to work everything out. And all these topological features we're going to compute are insensitive. They don't change to any order perturbation theory in G.
Right. But like my point was that the solution that we solved for like either the ground state of Z or this Wison solution is like physically different, right? But this is just like a certain gauge choice. So this is why I'm kind of confused. How is
yeah, well, so we went through that in the case of a pure Z2 gauge theory also, where we, in fact, in the current homework, you're actually computing dispersions in power series in G, at least of the Wisons. Okay, you can do the same here for this problem also. It'll be a bit more complicated, of course, but the same thing can work out. And yes, so yeah, this is a certain gauge choice, but the gauge invariant statement is, of course, that the product of Z's around this is -1, and the product of Z's everywhere else is 1. That's the gauge invariant statement. That's what characterizes a Wison. And everything I'm going to claim about a Wison only depends upon that gauge invariant fact. So you could choose a different gauge. The fact that there's a Majorana zero mode won't change. You could pick another set of -1s, as long as there's exactly one Wison, exactly one plaquette with flux of -1 through it. Actually, an odd number of plaquettes with flux -1 through it in this neighborhood, you would still have only one Majorana mode associated with it.
I see. Okay, so we are just like considering like excitation of this background gauge field and wondering, like, in the presence of this excitation, the Wison, like what is happening with the fermion modes on the edge.
Yes, we are certainly picking a gauge, but our conclusions are gauge invariant.
I see. Okay, thank you.
I mean, you always have to pick a gauge to do a calculation, and you just have to make sure that you did the calculation right. And then because the Hamiltonian was gauge invariant, you're guaranteed to get a gauge invariant answer. I mean, as long as you worked with a gauge invariant Hamiltonian to do the calculation, you're pretty safe.
Yeah, I can add one point is that you can actually move the cut around by applying the gauge charge operator GI. But in our formulation of the Z2 gauge theory, the GI is set to 1, so the branch cut can actually be moved to anywhere.
Yeah. Yeah, it just so turns out that at least for the Kitaev honeycomb model, because it has 2 electrons per unit cell, the honeycomb lattice, all these complicated factors having to do with the gauge charge of -1 per site don't come in. So the Wison properties under translations are very simple. But in principle, you could do the same thing for GI equals -1 that I'm discussing here. It's just more complicated. That's a separate set of phase factors you have to worry about. So there's phase factors associated with the translational symmetry. There's phase factors associated with the non-abelian statistics, and then you get, what would we call an SET phase and so on. We just consider the simplest case where, yeah, GI is 1 thing. Yeah. That's capital G. Remember, this is this GI. GI is product on links that belong to I of ZL.
Yeah. Yeah. Thank you. Makes sense.
All right, great. I think I'll probably also come to Hayo's section tomorrow, but in any case, I will also there'll be discussion tomorrow morning, and also we'll then finally wrap up our discussion of topological phases, cap topological phases on Wednesday, and then the rest. I think there are 6 lectures left, I believe. 1, 2, 3, no, 5. We were talking about quantum critical points and dualities. Okay, thanks a lot.